Thank you, everybody, for coming. We're very excited to host Dinesh Manocha from University of Maryland. He's going to talk about computer vision and robotics, and I'll let him take it from here. Thank you.
Thank you, Bernadette, and good afternoon. Thank you for coming to attend this seminar on a beautiful snowy day. I'm getting a Michigan experience here. It's a little bit cold, there. So thank you again. I'm really glad to be here. I've heard great things about this building, and thank you for giving me the tour this morning. It's a beautiful building and a lot of labs. So I've been working in robotics and planning for a while, and I'll tell you about the challenge we're dealing with. We call robot navigation in the wild, and what it comes down to. Okay. So before I go into stuff, let me acknowledge all my collaborators and students. Especially, I always say if you think I present a lot of work and a lot of ideas, if you have any good idea, the credit goes to my students. So a couple of my former students and current students there. We also have collaboration with a little bit of Google people. We have a big cooperative agreement, Army Research Lab, and also Amazon. So I want to acknowledge all my collaborators there as well. So this is, it's interesting to think of what is robotics in 2025. And you know what? I'm coming to robotics department, one of the first biggest robotics department in the country, and what robotics is about. So one good thing is, there's a lot of excitement about robotics, and including humanoids, right? Whatever it is, good or bad, if robotics is making good news, why am I complaining, right? Its hype is okay, but that's it. So all kinds of robotics is coming here, but this is not about humanoids. I know nothing about humanoids will do it. So robotics is a big problem, especially got amazing faculty and all kind of stuff. So the problem I'm going to be dealing with is a very classic problem that robots need to move. Of course, most times we move from point A to point B. You can take a generalized version, you're moving your arm, manipulation, but of the most time is moving in a 2D or 3D space, is something like that. So the challenge we want to make is that our ultimate goal is autonomous robots. We all have autonomous cars. I'm new to this campus today, this building. Even though it's snowing, if I have to go somewhere, I can probably figure my way around from here, right? And where it's snowing, how do I do it? So humans are able to do it, animals are able to do it. Can my robot move in a mapped or mapless environment freely? That's my ultimate goal. And of course, the motion should also be smooth and safe, no collisions and other physical constraints. We have to satisfy with that. Now, as I said, this problem is at least 40 years old or not longer. And if you look at today, you see such robots being deployed in daily life. So this is some, the restaurants, there's some Chinese restaurant bringing food to you, right? I've been working with Amazon. Amazon selling a robot called Astro. I know many of you people in Michigan also working on that. It's a robot in your home. This is George Mason. They bring food to you, plant a robot, and then their location like spot, looking at some irrigation operation, do it. So you see lots of examples. You sometimes go to the airport, you see a robotic vacuum cleaner, right? Now, what you don't realize is you see all this robot, you say, oh, this is a solved problem. Many of these cases are not fully autonomous. They're teleoperated. Even this food delivery, this is Starship and George Mason campus, they're teleoperated. And I heard that some of the people watching are in South America. So robots are coming up mobile, but fully autonomous is still a long way to go. So what are the challenges? So the biggest part is any environment, no restrictions, fully autonomous, safe. Of course, we always talk about robots work next to humans, right? So robots should be socially friendly. We call social navigation, collaborative system, not abrupt. Just like humans walk next to each other, robots should feel it. Now, as I said, the problem is not new. What's the state of the art? So most robotic example that you see in this example, like today, if you deploy it, either they're not fully autonomous, or like teleoperated, or they're autonomous. They only operate in a controlled environment. Looks like the display is having fun here. So just disappear. Let me play with this. Is it something to display right here? Sharing content with Zoom?
Yeah, sometimes I just need to.
Okay. We'll just reset it.
Should
We can do it here.
click on maybe.
Yeah, you do this magical tricks.
Yeah, unplug and plug.
I think the Zoom's switching the display between when people log in.
Yeah. There we go.
All right. Okay, thank you. So most use of robots actually are in environment which are not totally very challenging. They make it robot friendly, like warehouses. Amazon designed robots. The places which are friendly, they will probably not put too much glass. They put markers. They will not put environment. They make a lighting control. So that's the kind of situation where people are doing. Most application robot friendly, few humans, and they make their environment robot friendly. But the challenge is robots should work in our life space. Actually, I was here yesterday visiting a plant in Flint, about an hour away from here. They're assembling like the pickup trucks. And the plant is from 1940s, you can see things. And they say want to bring robots to automate that. So robot has to fit in your space. We're also doing some work with hospital robot assistants, some hospitals are new, some are old. Humans can go and navigate, robots cannot do it. So one example of this is, I'll tell you the example of a challenge. There's a lot of work on consumer robot. Some of you may have seen this video. We have a collaboration going on with Amazon, right? So Amazon picked up something very crazy. They want a consumer robot in your home. This is a version they announced a few years ago. They're working on a newer version. I know many people from Michigan also working with them. So this is the example of a robot in your home. It should come to your home, automatically map around, automatically figure out where to go and do things around. Remote monitoring like that. So something like this, what happens is everybody's home is different. Not only everybody's home is different, my wife complains I'm the most messy guy. I make different mess in the morning or evening. She joke, I'm a spatial temporal mesh generator. So she has to put up with me. I hope robot can put up with it, right? So you can see humans deal with it, right? Cables, put your bag, put your shoes, comes up there, edge computing, So this actually becomes a very interesting problem. I went to Amazon Lab 126. They have like a mock 2-bedroom apartment. So the question I ask you, I'm sure your students living in nice Michigan Ann Arbor apartments, which are not very expensive, as students were telling me at lunchtime. You got bedroom, living room, dining room. Which room in your home is the most difficult for a robot? With current sensing, something like this.
Bedroom?
Yeah.
Anything with glass.
Okay, but which room?
Living room, I guess? I guess it depends on the layout.
Bathroom.
Bathroom. It is bathroom. Because you got shiny mirror, glass, and you got a shower door. Now, why do you want robots in the bathroom? That's not the topic of the talk. Privacy is a very serious issue, but that's not what I'm addressing. But I joke, Amazon, they know my digital life, like what I browse, so they give me shopping recommendation. They want to know my physical life. So you'll get an ad, hey, your sofa needs a replacement, right? That's what Amazon will do to you. But this is a challenge we're dealing with. So yeah, your bathroom is tightly configured, challenging for robots. So this is an example of easy and not, we go to it. But other thing that also comes up you don't realize is that in this robot, when I work with them, so it's a $1,500 robot. They don't have like a Jetson GPU. It's a power supply. They're only 3 ASICs. So anything I do for planning with them has to run on a lower platform. We're doing some work on glass detection. You mentioned glass. We do LiDARs and all that stuff. They say, no, LiDAR is too expensive. So especially when you go to the consumer robotic, which I think is I told Amazon friends, like, you guys are most crazy. You pick the most hardest problem. We're a long way to go where robots can work at home. But this is just the example of people are trying, but where we are. Now, many years ago, I remember attending a conference in a workshop in Las Vegas with Mars with Jeff Bezos. In 2019, they were saying Amazon was burning about $27 billion for delivery budget in US. This was before COVID. I don't know, it may have doubled by now. And he said, could you even do 10%, 5% delivery by robot? Imagine something like Ann Arbor, right? Everybody order Amazon packages. Your poor shipping person come to every building, something. Imagine they come to the entry, dump a truck, a robot delivery like that. So Amazon had a project called Scout. They picked up together. This is an example of the experimenting, in your street, a nice street somewhere outside. Several come, robot come, you get a message, you go out and pick up the robot, pick up the item. So this was the example they tried to do. It's a nice example, but how many people live in a nice clean street like this? Think of the weather right now, right? Most of the world, so we have been doing a lot of work on robot navigation crowd. My own group, I have a former student, Pangaea, he's a faculty in Hong Kong. A lot of the world people don't live in nice clean streets like this. They live in places like this, a lot of humans. So this is something we are trying, robot with some sensing, and I'll show more results on that. where robot can go and deal with the messy crowds. So think of more streets in the different part of the world, and when can robot navigate in those streets, just like humans can, animals can, robots can't. So tell you how far we have to go. And of course, when you talk about robot navigation, the biggest interest in the last 10 years has been robot on the road, which is called autonomous driving. I even saw some nice one from Ford downstairs, right? A lot of people in Michigan, you got M-City here, right? So here we are, 2025. We were promised by Elon Musk that we'd have a robot taxi by 2016. That didn't happen. Somebody told me the VCs, the car companies, whatever computing companies have spent $70 billion, right? Google's Waymo, which is ahead of the game, they've driven 25 million miles in San Francisco. And some Phoenix, LA, they're going to Atlanta, expanding quite a bit. But they go and drive a lot of data they capture with LiDARs, and then also is Tesla. I also drive a Tesla myself, which is mostly cameras. A lot of work has happened. Now, the good news is today, now, after 15 years, there's a Waymo service in San Francisco, and nobody's tried it. It's supposed to be more popular than Lyft. That's what I've been told. Lyft, Uber is 55%, Waymo is 25%, interesting. And they are claiming now, in last May, they were doing 50,000 rides a week. Now Waymo is doing 150,000 rides as of last November. They're really growing, So if you look at Waymo's recent publicity, they just got $5 billion in money. This was as of November, October timeframe. These many miles they're driving, this they're doing. Now people thought, oh, autonomous cars have been solved. Actually, no. What you don't realize is these cars are remotely monitored. So when you sit in the car next time in Waymo, right, somebody doing, the only thing is that the way they interface is that the remote person may not be spending his or her 100% time on your vehicle. So they could be, eventually they're saying it only interferes with once every mile, or the corner case comes up. So coming up with a model where eventually one human could be watching N cars, which is still cost effective for them, that having a one driver, you have 1/10 of a driver. So that's the way they're growing. So this is after 15 years of autonomous driving, so much money comes up there. Now, of course, that San Francisco city is like something like this. When will autonomous cars come to Maryland or Michigan, right? Are we autonomous car friendly? Maybe it snows, maybe different weather. And of course, if you look at the bigger chunk of the world, this is a Waymo data. This is some video we got from China, You got traffic like this. A lot of world population lives in a condition like this, where people don't follow the rules. And it's all very high population. When can autonomous cars deal with situations like this? You can see the traffic density, people not following rules, heterogeneity, there are big vehicles, small vehicles. So this is where there's a big difference where Waymo is driving now to where we are today. So this is just to tell you how far we are to solve this autonomous navigation problems, the way to go. Of course, this sort of work we have done. We all know there are machine learning methods, machine learning rely on data. Of course, Waymo collected incredible amount of data. I myself involved in some collaboration. I'm originally from India, We went and collected some data sets from India. We took a bunch of vehicles with a bunch of companies. One was Meteor, which was published a few years ago. And the idea we try to tell people is, if you want to develop autonomous driving car companies, this is the classification of people can back and read it. There are different kind of, say, your bicycles, scooters, cars, motorcycles, tractors. There are 14 kinds of agents, not just cars. And then, different kinds of turn. People don't follow rules, wrong turn, this turn. So we try to capture the complexity of a more realistic traffic in big part of the world. And this is just data collection. There's no way we can do autonomous cars in this kind of condition right there. So this is the one thing. We also have another data set called DAVE. In fact, the term they use in the autonomous driving community called VRU, vulnerable road users. And the most one, those are actually bicyclists and pedestrians, the most challenging one. So it's another data set we collected and doing it. So if anybody wants to work on this thing, this is a long way to go, but at least we can do with this kind of situation. Now, for most of my talk, I'll talk about the recent work my students have been doing, dealing with difficult indoor situation, outdoor situation. And the different challenges, when an indoor building like this, the floor is mostly flat, except for stair. You got carpet or hardwood, that's good. The challenge of indoor thing comes up is two things. One is that you could have a lot of humans. So humans are the most unpredictable people, because human dynamic obstacles. And secondly, we get situation like we talk about glass. You got a lot of glass, my building, our building in Maryland has got a lot of glass, deal with it. We saw bathroom glass. Or sometimes you got situations like flexible or pliable objects. So with Amazon, the corner cases come up. Sometimes they see a piece of cloth, looks like cloth. They don't know if the cloth is part of a sofa, it's a furniture, or it's a hanging cloth like a curtain. Because the hanging curtain cloth, you can go through it. But sofa sets, you cannot. So there's just so many cases come up where you don't have a semantic understanding that make the problem difficult. So that's the indoor scene. Outdoor scenes are, the world is not flat. It's actually terrain is very uneven. So this is one of the biggest motivations, big project at Army, where they want to go in jungle. In fact, there's a whole organization called GVSC outside Detroit, which is Batar Deck, dealing with it. You've got uneven terrain, deformable, where to walk. Just like if you go out today, could you walk on that snow? If you have nice boots, maybe you can, or you cannot. Those kind of decision comes up. The second problem comes up with dealing with vegetation. So if I tell you something, here's grass. In your mind, grass is something soft. If you're well covered, you can walk through it. If I tell you the bush is hard, you won't walk through it, it's too hard. So in your mindset, this is bush or a grass there. Now, we got vegetation. The vegetation in Maryland is different vegetation in Michigan. The vegetation color appearance in January, February different than March, April, or July, or September. You got all kind of plants, all kind of vegetation. If I look at any random piece of vegetation, how do I know it's traversable or not? Soft or not? So material properties of this thing. So this is the kind of challenges we're dealing with. You come up here, and people have to do with these kinds of things right there. So I'll talk both these kind of situations, see how we're dealing with these challenges. Let me start with so this is the example of some indoor scenes, with the robot with the GPUs stuck in there. This is our building with the glass. You'll see the camera thing messed up, stuck with the glass. And if you go outdoor scene, this is our spot, like you have had our robots, we put the vegetation, and this kind of situation happens all the time. I'm sure you experience similar kind of things there to do it. As I said, there's a lot of work. This is a pretty well-studied area. There's a lot of challenges of perception and planning. Both are well-studied. You go to ICRA, IROS, RSS, lots of planning papers. You go to CVPR, ICCV, lots of perception papers. We build on it. I'll tell you what the challenges deal with it. So this classic planning, some of us who come up with example-based planning, model-based planning, optimization, I'm sure, Dimitri, we worked on this kind of things. So they work well especially they have good guarantees we can give it. But if you're given very dynamic scenarios, actually given very noisy world, because we're capturing with sensors, the sensor is not perfect. So this is where they work well, this is where they don't work well, you want to do it. Now, of course, in the last 7-8 years, this whole area of learning has exploded, and we were having a lot of discussion on learning. There's a whole conference called Coral, which gets about 1,500 people who want to attend them. There have been lots of learning methods. You pick up supervised learning, imitation learning, reinforcement learning, feeding LLM. Now, they all depends on, if you have a lot of sensor data, uncertainty, they can deal with it, they can dense setting, but of course, they all depend on underlying data. And secondly, you cannot give interpretability. Like you cannot give guarantees. You don't know, you change the condition and what will happen. And we all have experienced that. And of course, most of this is planning, we are thinking, but if you go to the perception world, which we do it, now perception, all successes we have seen in the last 10 years are based on, deep learning and other kinds of learning methods. So here, perception, in fact, I'll tell you up front, a conclusion, in all the autonomous system, I still personally believe the biggest challenge is perception, scene perception. There's so many cases come up. And of course, learning is helping up, but semantic understanding of the scene perception still remains a challenge, and we deal with it. So we are doing these kinds of algorithms, but also want to mention that a very important part of robot, we all buy big GPUs for training on big H100s, but here everything happens when on the edge. So the edge requirements actually comes up when we're doing our system with autonomous Spot. I had a smaller GPU, I could not run my latest transformer architecture. So a lot of decisions have to happen, power supply. So robotics comes here. So in the rest of my talk, I'm going to show you how I work on indoor scenes, outdoor scenes. In the time permitting, I'll tell you a system we built a couple of years ago, an autonomous excavator, which how ideas can come together, we do it. So let's talk about indoor scenes. So with the indoor scenes, I say, if the floor is mostly flat, that's okay. Static obstacles, we're getting to a stage we can kind of deal most of them, unless some very challenging cases come up here, right? But the most difficult situation for indoor scene is dealing with crowds, humans. In fact, and before I used to do like, I don't know, work in graphics, and this situation deal with crowds. So you have, we call densities of crowd, if something is moderate, less than 1 person per square meter, 1 or 2, and some gets very distant. So especially one of the challenge we're dealing was, can our robot navigation deal in environment with dense crowds? How dense can it get? So there are some parts of the world get very dense, there. And there are a lot of challenges. We want to definitely avoid collisions. If a lot of people are moving, we humans are very good at looking at the humans' motion, anticipation, and plan. Like humans are pretty good at it. Can robots be equally good? And one problem in robotic will happen is called freezing. They say, when you're not sure, just stop. Remember there were all the stories of in Waymo or cruise cars, a couple of in San Francisco, they'll go to intersection, get confused, and stop at the middle of the intersection, which causes traffic chaos. So your freezing can be damaging. So trying to deal with, how do we do it? And in fact, we did a lot of work on, simulating crowd densities, we do that. So in this case, we say, have you developed a system? Let's look at the pros and cons. So there's a lot of previous work. All the actually optimization-based methods, sampling-based methods, I say in some way, they're good interpretability. We know the math behind it. We understand the pros and cons. This is good. But they could not deal with something very dynamic, scenes with a lot of moving crowd, humans, the densities unscared. In fact, because the perception is based on deep learning, how do we bring it? If you bring a learning-based methods, they are much better dealing with uncertainties, but they have all this problem of domain gap interpretability. So to plot this together, we said, what is good here is not good here. What is good here is not good here. What if we combine, take the best of both worlds? So this is the kind of approach we are trying to pursue. I think learning is great. It's just not the perfect solution. So what is great about learning? Let's exploit it, but let's compensate for what learning cannot do. So that way we can best of both the worlds. And the second thing was we're dealing a lot with what we call social navigation. We want to make sure that the robot walking next to you is acceptable. So actually for this kind of situation, you need a lot of data, human data. So I exploited our previous work on simulating crowd, which is very popular in games. And we had a crowd simulator will just take a lot of synthetic data. And this is actually one place I would say synthetic data actually work well. So this is, this is actually my, I know it's recording me. Okay, fine. It can't scribing me in real time. All right. So if you can't hear me, you can read it, right? I just noticed that. All right. So this is the thing, and they actually work well. So one other thing you notice, people don't realize that when you go to a physical world, if you go to a mall or like a student union or like an airport, most 70% of crowd is some kind of a group. It could be 2 friends, could be a couple, family of 4. So this is observed by social scientists that a lot of crowd is group. And what does group means? If you're a part of a group, you have a similar goal, like a couple is going to the same location, probably walking at similar speed, have similar patterns. So one thing we also want to do is use our computer vision method to detect groups and use the group property to navigate. You don't want a robot to go between the groups. It's kind of socially acceptable, so just humans will do it. So literally what we've been working on a lot of method for learning. In this case, we did this a couple of years ago. We have reinforcement learning method and also did a lot of work on optimization-based method, geometric optimization, something we did it. I won't go into the details of that, but this was a typical learning. You do it, here's your prediction model, you play with architecture, reward function. And as I said, we use a lot of synthetic simulation, which in this case work okay now. So the real gap is here, but luckily in this case, we're not doing it and it does a good job. So this gives a good part of learning, but you can't predict. Learning, DRL, if suppose different configuration of people come up, it may not work well. So I go back to many years ago, about 12, 15 years ago, we worked on a lot of geometric optimization method for collision avoidance using velocity obstacle, reciprocal velocity obstacle, and something like that. So the idea there is the following, you're like a 2D plane, you approximate each human by a circle, it's a close approximation. And this is your robot position on a 2D plane. You basically look at how each pedestrian is walking, and you want to figure out how pedestrians are moving. How can you move so that you don't collide with them? It's kind of a conservative condition. And this turns out to be posing, strictly speaking, it's becoming quadratic constraints and like nonlinear constraints. You can say the optimization solution to that. You can take the quadratic constraints and kind of conservatively approximate them a linear constraints to make it cheaper. So this way, if we say we can find a feasible optimization solution, we can guarantee the robot will not collide. It's kind of a scheme, and that's been very widely used actually in gaming quite a bit. So this is how we actually do optimization real time. So we literally look at the method from the learning method, starting position. We look at computer vision real time, because the vision detectors are getting really good. Sometimes yellow pedestrian detectors are really good. The latest generation, we exploit them if condition is good. And ultimately, we look at different pedestrians and we figure out the motion, this pedestrian moving in a direction which could potentially freeze and also non-freeze. No collision and no freezing. So we come with conservative condition and define what is called potentially freezing zone. And if you're outside the zone, that's a sufficient condition. So this is just a high level stuff, but literally the way it works out this way, you got a whole bunch of pedestrians, you look at their motion with the optimization method, and we think this is a potentially freezing zone. In the real world, it's my robot with a 2D LiDAR and cameras. This laptop is for GPU. We do potential freezing zone, conservative zone. All I'm saying is if I stay out of this zone, I can guarantee non-freezing behavior, a conservative condition. So this is how we're also making sure we take the vision methods and do it and make up for the compensation. Now, typically you do situations like this, you have a lot of ideas, you don't want to test robot in different situations. We want to see how many times we get frozen and how friendly our motion is. The friendliness comes up with some constraints like, how you metric, like pedestrian fit, there are different metrics now. You do a lot of situation conditions like this, look at the thing, how they work out, like typically you have a comparison like this. So I'll show some examples. This video is actually about a couple of many years old. So this is a lobby of our building, just a beautiful lobby here. It was a crowded scene, a turtle bot with a 2D LiDAR camera. But see, when robot come to your environment, people can do crazy things with it. You saw a robot rolling around, right? See what people do. And this is literally, the robot at a height of 2.5 feet watching the thing, but literally is able to walk very seamlessly in this kind of situation. So this is the example of some combination comes up. This is showing our synthetic data training with depth camera and LiDAR, different situation. So at least we demonstrated, that in a very pretty crowded scenes, we can indeed do it. Now this is showing the freezing behavior. This is a different robot. We took a Husky. Again, you will see some same sensor, LiDAR. And in this case, is watching them compared to the potentially freezing zone and trying to make sure it doesn't collide. So looking at how pedestrians are moving, doing very good prediction, and based on prediction, doing a navigation, which is non-freezing and socialized. This is taking a lot of ideas from learning, perception, and reinforcement learning for planning and optimization to get this kind of a good behavior. We can do it. Yes, question.
On that video that you just showed where it was navigating between two people, it seemed like it was persisting on staying on the red path when there was someone it was about to collide with. So
this one?
Replanning whenever it's about to collide with someone, or is it?
So, right. So typically, we do locally at every stage. So you can have a configuration, you can switch there. So it literally look a short, in this case, doing short horizon part. So that situation can arise. You can go like this and suddenly happen, you readjust. So you can go in like this and suddenly you see a situation because the freezing zone is conservative, it can conserve, and then you suddenly stay itself. So that abruptness can happen. This part there, yeah. That's one thing. But this is just so much with the indoor scene. This was actually showing, yes, reinforcement learning with good training data and potentially think and do well. Then we went ahead with, as I told you, a lot of real world crowds are group properties. There's again, we do some metric for everything there. Computer vision methods. So this is one thing I would say, the vision technology has become really good. I told YOLO-like, these detectors have become really good, so we can do it. And we do the same methodology we can do. We detect groups using computer vision, define a potential freezing zone for a group, and similarly compute a velocity, which is not freezing and not colliding with the group. Similar kind of thing. Here's like a simulation. This is like a simulation. People are moving, we're making dynamic groups, shown with the color red and blue. So we can do different simulation and do this kind of prediction of dynamic groups are forming. Even in this case, we can do it. We didn't do this one extensively testing a few years ago, but at least a few settings, you can do it. If you do big testing, you can do big IRB problems. So I just avoided that, but tested it there. But this was an example of showing that we can indeed have robot system. We can deal with crowd, which is one of the big challenges there. Now, this was a system that definitely used a lot of sensing and a lot of deep reinforcement learning. So you can see all my robots had a clumsy laptop tied up because doing GPU on a good laptop that time. If you go to consumer robotic, I work with Amazon, right? So Amazon announced this Astro robot, which some of you have seen. When you consume a robot, it gets a lot of reviews on the internet. So when you somebody's condition, you don't know what situation will come up. So-
Through is much, much smaller.
So-
First off, it doesn't bang into my feet at the time. Instead, it's able to follow me around without getting in my way. It rarely gets stuck, besides that one time it came fixed.
So this is somebody reviewing the configuration, it happens here. Secondly, is a perception, because everybody's home. They have different lighting, different shading condition, different outdoor scenes. And they thought is that in some cases, mapping affected by lighting, glass, and shiny floors. So some example of a transparency. So this is what I say, this consumer robotic is actually the holy grail. It's the most challenging among all problems, because working everybody's home so different, robot has to adjust. So this is our work. We've been quite a bit with Amazon we're doing, so they wanted a solution which can deal with glassy surfaces and also deal with, difficult configuration.
And while a robot vacuums,
So one of the things we have done recently, we have a new method to deal with glassy and shiny objects. There's a good thing and not so good thing. So the good thing is we actually use a 3D LiDAR. Earlier I've done some work where you look at glass and some sonar sensors. But the sonar sensors are a little bit orientation dependent. If you've got a curved moving glass, it can not be reliable. So that was it. So we actually went for something with a 3D LiDAR because it's 360, so not orientation dependent, and also doesn't depend on lighting. So we have we use a multi-level intensity map, and like the roots of this come back, from my graphics background. If you take a graphics class, it teaches something texture called MIP mapping. I don't know if you've heard about that. We took those ideas and make multi-level intensities, and we showed that with the multi-level intensity, you can do glass detection with mapping. And guess what? There's no machine learning involved, and it runs on a low-end CPU. We actually submit this paper to CVPR, and they say, no machine learning, we won't accept. And a joke, we go deep learning, how can you do computer vision like this? That was it. But anyway, but we have tested this on our campus. We've gone to all our campus buildings and tested it quite well. It's like a very cheap low-end CPU, run it here. And we have really tested well different lighting conditions and doing things around this. So this is for our system. We're comparing with the real-time detection on this thing. And we have found it works pretty well. So this is a good glass detector, at least in our experiments, it works well, 3D thing. But my Amazon friends are not happy with me because they don't want to use the LiDAR. Firstly, LiDAR is expensive. And then secondly, saying it's a consumer robot, anything a consumer product should at least last 5 years. They are not sure the varifocal mirror will last 5 years. So this is, again, the challenges comes up, right? But I'm hoping somebody will come with a good and cheaper LiDAR, this thing. That was it. Secondly, they come with a problem of dealing with homes. Homes have all kind of furniture configuration. Think of between the two tables there. Narrow passages come up. You move chairs around. So they wanted a much better planner. And as I said, the deep reinforcement learning was not an option because this robot only has 3 ASIC chips. They're not really as flexible. So I cannot run my DRL, the network I showed you, on those ASIC chips. So they wanted a more reliable planner. So we go back, I'm sure all of you take a planning class from Dimitri, everybody, you learn about this undergraduate class, MPC, motor predictive control. So we looked at ideas of motor predictive control and literally go back and do it. The good thing is, these planners can run on very simple chip. You don't need anything like a heavy GPU again. That's again a good thing. So we did something called MPPC, work at John Park, XMDS MPPC, literally doing much better collision probability, leaving in narrow passages and T corridors. So these are difficult situations that come at home. So actually Amazon went ahead and they were testing it up. They did a big science announcement there. So we did this joint work with them, and this was appeared in ICRA, but they did a science release. So this is, let me see, I don't want to detail with all the. So this is just the details. You're welcome to check out the papers for collision probability term. But this is, you can see, very rigorous stuff and do it. And this is some example you show, like a narrow passage. This was the basic correlating method, where to go and get stuck. But our new generalized collision probability does a better job. And you can do very difficult configurations and show that MPC ideas can be extended to deal with it. So again, those of you machine learning, you can do a lot of good problem without machine learning too. So this is an example of a sofa set like somebody's home. A tight configuration, the previous MPCs will get stuck, will slow, but with the better collision probability estimation, we can do this situation quite effectively. So this is, they have been testing, they have a lot of test suite. So this is trying to show again that yes, we can do good planning with this kind of problems in different situations. You'll see different testing with Astro Robot, and making work on Astro is actually non-trivial. They don't have API. You go to Amazon Lab 126, Masur intern, dealing with situation. but we try to show that with active collision term probability, you can do a pretty good job. So this is so much, yeah.
Other than computing constraints, what extra benefit do you think the MPC-based versus like a DRL approach has in situations like this?
Well, as I said, MPC is more like a model control. I can give some guarantees. So I say if this condition is satisfied, certain condition, it'll like a lot of optimization-based method, it will not collide. With DRL, it's all about learning distribution of data. So if you change the configuration slightly bit, so learning is great, with sensing data, but the biggest problem with learning method is interpretability. So if you give me new you change the chairs a bit, and I say my DRL work great, if you change it, it will work great, I'm nervous. So that's the channel learning, right? It's a new configuration create a situation which is automatic distribution. So this all machine learning method has this so data dependence, and those distribution are very hard to quantify. So that way MPC was also better. But again, in this case, you had the perception, you had a good perception. But if a noisy data comes up, the DRL methods have benefit dealing perception. So I would love to deal with both, but in Amazon Choice, I didn't have the compute budget for the DRL methods. But that's what comes out of it. Any more questions or feedback? I love questions. Please feel to ask me anytime. Okay, so let's go to outdoor scenes, right? Life gets more challenging. So what happens in outdoor scene? The two big challenges come up here, right? Outdoor scene. One is that your surface is no longer flat. Not nice flat hardwood, not flat carpet, right? Terrain, snow, you name it. One of my goals is, you go hiking, you do it. So there's texture, bumping, and semantic segmentation. And secondly, you're going through vegetation. This is just next to our building in Maryland, like a rough area. And literally, how do you vegetation that can my robot go through this or not? As a human, you realize this is not dense and this is soft, you can go through it. But for me to figure out what after the grass versus bush analogy, the material properties. So one of the challenges of computer vision is it can recognize object, but it cannot tell me the softness. Like I told you the cloth example. So Amazon cares about the fact, is it a curtain, tablecloth, or a sofa? Same thing with vegetation. So this is the challenge that comes out to be there. So you take robot, we take also export robot, we put our own GPU, NUC, and sensors, 3D LiDAR in this case, and do it. So what are the problems that come up? You first will have something like, you come here, the robot come up here, misclassified, there's a collision. Second thing you do it, if I'm not sure, in fact, if you buy a spot robot and you test it outside, does it sometime, you see this condition here, it'll come, it's not sure, it'll just freeze. It's like, okay, I'm not sure, I turn around, that's not an option. And the third part is when you see vegetation on the bottom, you can classify them mathematically, the entrapment that you come here, it goes there, these weeds get stuck in your joints, and it gets missed. So there are a lot of environmental complexity that come with outdoor scenes, which makes it hard. So many of my students are obviously dealing with this problem, and I will not go the details of that, give an idea that, so we take into account the physics dynamics of the characteristics of the robot, because I deal with a small robot like a husky to a legged robot like a spot egg horse, and maybe with a few that have a humanoid, big humanoid, small humanoid comes up here. So we do it. Now, in computer vision, there's been a lot of work on semantic segmentation. We use that. Like segmentation is getting really good. It can tell you, oh, this is probably the pavement. You can go over it. This is grass. This is weeds. It can do it. It's getting there, but still it's not enough, because what is traversable for one robot may not be traversable for a robot. So we rely on computer vision segment, but we're actually looking into navigate by correlating a robot observation with the surface interaction. So you've got visual sensors, visual segmentation, but the interaction between the ground and the robot, the physics comes up, number one. The second challenge is identify vegetation. Now this is still, we've done some work, but again, up front, this is a challenge. Instead of, we don't have a lot of ImageNet like data or vegetation vetting, and vegetation just varies throughout the planet, different time of the year. This is a really big challenge. So we are trying to do some comparison stuff, but each other and try to make a guess of which vegetation is traversable or not. This is anywhere from being a solved problem, a deformable thing. So also there are data, we develop a whole bunch of traversability method. Basically, you look at the information image, and we come up with like a some kind of cost map, This part is traversable. We classify surface dark map with like blue labels. This part is more rough, not traversable advisable. We do it by yellow. So we also developed, since we got our data, a whole sequence of self-supervised methods. They're all published in last couple of years, comes up there. And I said to you, that was the segmentation part, but we also tried to do interaction with the robot and the ground. So this is looking at interaction, in this case, doing simple PU analysis, PC analysis using IMU data, interaction. And based on that, we augment this with the segmentation information to make the decision. So this is just showing working. Here's like a terrain map you hear. And here you will see it's kind of working the basic real time. So on the top is your real terrain, pavement versus grass. And you see how we do interaction and classifying. This is traversable, this is non-traversable, soft surface gauss map. This is happening in real time. So based on the sensing, this computation real time, and using that to go out. So if my robot goes out today, hopefully I haven't tested snow, pavement is good, snow is bad, do go there, low cost, high cost, we do it. We'll love to try it because we haven't had much snow in DC, thank God, to try it out yet. This is an example of comparison with different methods here. You see this here, this is our latest Terrapin. If you publish any paper in ICRA or Vision, reviewers want to see comparisons. So this case, we did a much better job at traversability. This method did not work well. So they did a good job, they will get stuck in dense vegetation or logs. But our method, because of the better surface map, with better traversability, and therefore it can go with difficult terrains much easier. Yeah.
Are you using the IMU data to label the traversability?
So with labeling, it's very hard. So we use the visual data, like the cameras and LiDAR for segmentation. I am using for interaction. So the cost map we compute is a function of the visual segmentation and IMU interaction both. It's a combination of that.
But what does it mean, IMU interactions?
So basically, you got this IMU, like, the sensors. We're trying to get a feeling of, it's a very coarse approximation of how the robot interacting with the ground. It's a very coarse approximation of that.
But you are using this as a proxy of the traversability.
As one of the information. See, I still have segmentation. I still have semantic segmentation.
Based on
Computer
other data
vision.
train.
Yeah, computer vision.
Train.
Yeah.
You already have concepts, grass, snow.
Well, so there is some segmentation, hard versus soft. But the point is that even if it's grass, depending on the robot I'm having, sometimes if it's a big heavy dog, it can walk on the grass.
Mm.
But if a small turtle bot, it cannot walk on the grass.
Mm.
So even if I know it's a grass soft, but is this grass traversable or not? The segmentation does not give me enough information. So for the other part to make the actual decision, I use IMU data for their classification. The robot dynamics take into account that.
But you are showing the map is this blue,
Sure.
the green, the yellow.
Yes.
That
That is segmentation only.
is just segmentation.
Yes.
And how are you using IMU? You're using IMU data to learn the right policy?
No, IMU data is to account for robot dynamics physics.
But how is it, what role does it play in the whole pipeline?
Decision making. So even if, see, this is a segmentation map. This is giving a cost map. Okay, this is like, let's say, the blue is called the low cost, and this is called high cost, just for it's a subjective thing. Depending on the robot, should I go over yellow region or not? The decision to make. It just tells me segmentation labels a high cost.
Mhm.
But segmentation doesn't tell me, is it traversable by robot? It's not sufficient to tell me that. And that's why I use IMU, the heuristic to guide in that one.
How do you incorporate the IMU data?
It's in the learning network.
Learning, but where do you get the supervision? It's doable, it's not doable.
Well, so, okay, let me answer that question here. I see, I'll come back to it in a second. So we basically looked into different classification of surfaces. We ourselves experimented that and we labeled it ourselves.
Okay.
Yeah, so that's what you're
That's
asking.
the eventual knowledge you count.
Yeah. It's so the learning, that part is, you can call it as more like a supervised learning.
Okay.
That's what.
So Phuket at MIT has some active sensing.
I'm sure people are doing new methods. That'll be great. In fact, let me answer your question in 5 minutes.
Yeah.
And another method, we are doing proprioception.
Okay.
And sensing is a very challenging. Let's just give a couple of minutes, I'll do that. So this is the second thing I tell you, variety classification. This has been a very challenging because, as I told you, we use the term actually, my students call it pliable or non-pliable. Pliable basically means it's soft enough. Non-pliable means it's not soft enough. And this is, again, like a material properties, right? And again, I would say one of the challenges we are facing right now in robotics is that for a lot of tasks, we need material property and computer vision not good enough. In fact, there was some nice work from Meta. I don't do work on manipulation, but they're also doing manipulation. When you grab something, right, this is soft, this is hard. Humans' hands are very good at it. People are also trying to put cameras. So there's a lot of work going around, right? And maybe active sensing is the way to go, that anything you sensing which can tell me material properties. That is still a big challenge for us. And I'll come back to it. So in this case, at least we have some heuristics. We did pliability there, you know. And the example you see, sparse cut, dense cut, bush, tree, right? There's a whole spectrum of vegetation you can do. We have some heuristics, not the greatest one. I'll just show you some of classifier we have done. And we basically do comparison, came with some heuristics which can do it. But also the thing I told you about that multi-level intensity map, that itself is good. But one challenge that comes up is I look into grass versus like a wire fence. So with computer vision, they both look thin structures. Grass is soft, wire fence is hard. So there are always these challenging cases, you know, we're still struggling with perception part, what comes up there. So this is where things have to be there. So there's one of the big challenge I would say for perception is semantic information and the softness or pliability. So this comes the other part, we're looking quite a bit more into this question. So we have all the visual sensors, LiDARs, camera, exoception. If you do go out today, if you look at that snow, but probably you will put your foot forward and get a feel of the softness. Unfortunately, my robots don't have good tactile feedback, whether it's walking robot, whether it's grippers. So our sensing is very limited in robots. So in this case, what we try to do, again, this is the question you're asking, we do proprioceptive traversability estimation. How do we do it? This is for robots. We augment that with the vision sensors. So in this case, we look at the robots. Let me show you here. We look at the vibration analysis. This is again, we do proprioception followed by extra camera sensors. So again, we did some kind of like a supervised pre-training learning. So here's an example. A robot is walking on like some kind of a sandy surface, right? This is our old previous system, the only computer vision, LiDAR and camera. This we augment computer vision with proprioception. And saying, now, how do we do the same question that you were asking before? We are looking at this vibration analysis mean value of the cost. So we are kind of doing a call like a pseudo haptics, right? So this is surface or not, but based on the vibration analysis here, I adjust my robot gait. So I make a conclusion: the sand, walk slowly. It's like imagine you figure out it's ice, you may walk slowly, you gait. So this is called proprioceptibility reversibility. In this case, we're doing the vibration analysis to figure out and go around it. This is another kind of example of a sensor I was doing. Combining this on top of the visual sensor, we can do much better job at traversing. In fact, you can see, we look at this condition, you got rocks, you got, you know, different vegetation, and here it will slip but with this one slow down slowly, so it is less slippery. We adjust our gait to deal with the environment. So this is the kind of example we're dealing with quite a bit here, you know, and see how far we can push it. In fact, my collaborator army have all challenges. They won't deal with really muddy places. And how muddy is mud? Soft mud, hard mud, we can talk about it. There's so many situations, like you can see difficult terrains, especially after snowfall-like thing, which becomes a nightmare for robotics. Though still, I don't think we have a robot which can walk around Michigan campus today reliably. We're not there yet, but there. So this is some of the work we did. This is our work with Army people. So this was a couple of things they want to show up. This is the Grace's photo location. They actually left a part of the grass totally untrimmed. You may not be able to see it. This grass is 4.5 feet tall, almost 5 feet tall. You can't see the scale, and very dense. Luckily, this was on a nice sunny day, so no mud. Made my problem simpler. And we also sort of made sure there are no big hidden rocks or trees, because there could be a lot of things below the grass you cannot see. I was actually talking to some people, General Dynamics, and they want to Army this big problem in the Army called off-road autonomy. Because this is not a clean road, you do it. So we will demonstrate there. So this was like our robot with a GPU with this thing. And you know, when my robot goes in, this is expensive. It's like my baby was saying, I put a flag. If I can see the flag, Okay, my baby is safe, you know? That's it. You can see how much trust I have in autonomy. So this is, they want to show there's a lot of journals there, you know? So we said this is totally autonomous, it avoids a human, this is the easy part. But looking at a lot of these MAME ideas here and figuring out what graphs are doing. So this is without, we're doing some proprioception, but we don't have very good haptic sensor. What humans will do, you use your arm, hand to figure out the hardness. So this is the kind of vegetation we're dealing with quite a bit and going around with dense grass. This was one of the first one to show it. Then more recently, we showed something like this, is an example of a much longer terrain. So they pick a longer terrain, it has grass, it has a fallen log, and all kind of vegetation. So this is the same video. This is a camera, this is a ghost robot, on the top of the ghost robot, and this is like the same camera on the behind. You'll see the same view, this high resolution, but see how they walk and go around. But this is the view of a robot camera here. And this is actually the whole navigation happening. So it comes here, it detects the log, it adjusts the gate slowly, automatically to go over it. So this is like detecting obstacles and trying where to walk, you know, for a robot. This is safe, this is not safe. This is exactly, it's like a grass on your ear and your face, and you're deciding between them what increase. So these are the kind of difficult situations. This is what I call navigation in the wild. You know, you go hiking, right? Can my robot go hiking? And there are all kinds of situations in, you know, DoD, everything. They want to guard borders and everything else, very difficult terrains, and they want to cover by robots. So this is still we are still a long way to go before we are reliable robots, something like this. And of course, you know, we are being a lot of discussion today with multiple people. We're living in the world of VLMs, right? Everybody thinks the hottest thing in the world is which VLM you do it. So, you know, VLM is the interesting thing. The way I look at them is, you know, somebody like the Googles and the OpenAIs and the Meta has spent a lot of money and a lot of internet data to train it. It's not the perfect thing, but you know what? Can I do something useful with it? So we are trying to use VLM, especially for a couple of things, because we have a lot of perception cases. You know, I don't have data, and my one vegetable classification is not the most robust one. So we're doing two things here. One is that we're doing what VLM for this thing. And secondly, we also want to specify behavior. Like by telling you, robot, go walk outside, don't go on the grass, do this, don't this, do this. So also for the language part, the VLM part is really good. So we're literally trying to combine those methods here and see how far we can use VLM. This is some of the work we've done recently up in ICRA, you know. So you have preferred U for terrain, and define a generalized approach which can also exploit different navigation behavior with language instruction. This is again architecture. I will, you know, not bore you with this on top of, you know, different, because behavior-based planner specification. I'll give you an example, this will do it. So here you have a situation similar I showed you. You look at the terrain, you do the cost map, you know, blue is the good part, yellow, green is the other good part. You're doing a navigation, but you give instruction a robot. Be simple language, stay on the sidewalk, follow the crosswalk, avoid the grass, and stop for hand gesture. So for this kind of language part specification, the language part of the language model come very good. So here's the example you'll see it walking here and actually not only doing traversability as we talked about, but following the additional constraints that come from your language specification. So in this regard, VLM has some benefits. You know, especially if you want to bring the language into robot navigation guidance, VLM can definitely do a very good job. I think language is the best profile of VLM, and we do kind of situation like this here. So I show some more examples here. This is, you know, we'll do it, but this is an example of, you know, different situation, how the behavior changes. So you'll see similar environment. We have similar this thing, but we change the instructions here. This is a camera view. We change the instruction, avoid the grass, stop sign. How we change the constraints into account and how they change the navigation behavior. So we're doing auto navigation along with language specification behavior and do a good job. I think I'm running out of time. Let me just show one last project, which you do it. I was involved in this quite a bit, but I want to show you an example that while the general purpose autonomous navigation is a hard problem, there are still some applications which are in our reach today. So that's a positive need. So many years ago, somebody approached us with our bio research, can we do autonomous excavators driving? Now, excavator, you know, it's like a good VC talk. It's a huge, big market, $70 billion. A lot of excavators are used. A lot of excavators are used in mining or different situations which are very hazardous. They have natural disasters. They could be toxic soil. And sometimes they work 24/7. You know, very, very inhuman situation is good. So we took excavator, and this work was published a few years ago. We started putting all kind of sensors, right? You put your LiDAR, camera, RT, pressure sensor, inclination sensors. It's kind of like, you drive by wire, you go and do it. Now, this was the example of, to make it work well, this was a team of 12 people worked over 3 years to build an autonomous system with perception module, planning module, and control. We have a paper which gives all the details of that. Literally, we want to show, can we build excavator for the jobs like, soil transportation or digging, getting human level efficiency, but we didn't want to just show something. We want to build an excavator which can even work 24-hour non-stop. We want to show reliability. In fact, this has been deployed. Now, this is again, going in details of this, I won't do it. They're all the sensors here. So typical robot, you got sensor LiDAR, camera, inclination, pressure sensor. You got a lot of perception, 3D LiDAR perception, 2D perception here. We all motion planning to high level task planning. We give out a high level job of perception, break into motion planning job, and eventually we go and do this. So it's a very complex system building to put it together. And the goal was how well you can do it. So this is an example of a human driving a Caterpillar excavator do it. Of course, they take a thing, the expert person know how to control it, get a big chunk of the sand. They want to cover maximum efficiency for transportation, do it. And this is our autonomous excavator actually working on a toxic sand, working on it and doing it. And we actually measured sometimes you're getting about 80-90% efficiency. As you train more, you can do better. The challenge of this also comes up the following, when you work outdoor, environment becomes a problem. You have a dry soil, wet soil, big rocks, rainy, heavy rain, small rain. You get all kinds of situations. Most excavators don't work in like nice, clean places. So how do we deal with it? They do it. They did a big release a couple of times. There was a big press conference. They tried to show this, it's like a big thing. We got a media coverage. It goes there, it works, it's doing the job. And guess what? And there's like no human. So this is an example of one place, where if you put technology together, you get a lot of right data, you can do something useful. I'm not saying it's perfect, it's not useful. And this is an example of, like an excavator working here. And this is the view where a driver would have sit. So this is the outdoor view from here. This is the camera view from here. You're sitting here, and you can see how this will work. And literally, this is what it showed. But we want to demonstrate that it's not just work for 2 minutes for a paper, like we cherry pick pieces. It can be reliable. It can be quite a bit. So we put a test, this was like a mining situation. It can work 24-hour nonstop. So here's the example of a thing. This is a situation in the soil at midnight, 6 o'clock in the morning, 12 o'clock in the afternoon, 6 p.m. So you can see it's working nonstop. Even though there's a constrained environment, a lot of cases comes up, and eventually you can see how the job has progressed. And you see there's nothing here, and how it builds up here, it goes on there. So this is an example to show that indeed, there are situations, if you bring right level of perception, planning, and control, you can do something useful. It's not as perfect as a human thing, but it's getting 80-90% efficiency. Now, somebody asked me, how do you compare excavator to autonomous car? One thing I tell people is because when you do construction, you kind of seal the site. There were no humans here. Unlike the cars, right? If there's human, I would not trust my excavator. That's my faith in computer vision, right? Let's be practical. So if you can constrain your problem, right, then you can make autonomous to work. And it's funny we talk about having the discussion with Dimitri. Nowadays everybody's talking about humanoids, right? It's just every day in the media they knew about humanoids, right? So this is, I have a very interesting viewpoint to it, especially US they come to like figure something. But I was at a conference in Abu Dhabi. There are 30+ companies in China working crazy hours, because of competition coming new hardware. So good thing will happen, I think, is that you will get some good hardware. Sorry, Dimitri, I'm not sure about the hands, but the good locomotion part will come up. So I see this as a positive development. You know what? If they're putting their money and giving us researchers some good hardware, why should I complain? I'm not saying it'll solve my problem, I will tell humanoid, but let's see what it is. But what I want to conclude is a couple of things, So our goal is to build autonomous robot system navigation, right? And I showed you a whole bunch of 3 or 4 examples here. I went through quickly. First, I showed you work on indoor navigation with crowds. Maybe use reinforcement learning along with optimization. I showed you our work on dealing with outdoor terrains, with vegetation. When we were with Amazon, they have different hardware constraints and sensing constraints. We deal with that. and excavator. So, gone through 4 kinds of attempts we have done for autonomy. And for each situation, we have different solution. Like different sensing, different outdoor terrain, different problem indoor crowd, different problem on excavator, different problem with Amazon. So there are all 4 examples out there. And one conclusion, what have we learned here, one is that I will tell you clearly speaking, developing fully autonomous systems is hard. Forget the AI hype. This is physical AI, okay? So developing fully autonomous systems is not simple. Everything, a lot of challenges comes up there. And literally, as the world gets more unstructured, the life gets harder. And this is what autonomous car companies have learned the hard way for navigation in the wild. The one challenge comes up here is, I would say, traditionally, there's a lot of work on computer vision, computing perception. We robotics people do planning, control. When you integrate the 3 modules, which I was doing in all the systems, the problems compound. So if I go to a computer vision conference, I say, 98% accuracy, wow, great thing. But as a robotic person, I worry about the 2% it doesn't work. Because those problems compound with me. So in autonomous system, one of the challenges is integration there. And when you integrate sort of thing, you're governed by the weakest link Amdahl's law. And so far, the biggest link in our system has been perception. The semantic understanding, the softness, that's what drives it there. And of course, as I said, these are examples of physical AI, right? And physical is unforgiving. In fact, as I said, a lot of people, including us, start using VLM, LLM because it's cool, it's fashionable. But there was a thing we found out, a paper that actually this can also exaggerate our safety concern. VLM have their own can of worms. We're still discovering that. So this is there. In fact, just to conclude, we put together a book last year, we did a survey of this thing. We look at different methods and literally the conclusion of the book was this whole area of developing explainable and interpretable learning or robotic is still a hard problem because humans are very good at dynamic adaptation, but the current AI models are not. So for all of you who are doing PhD or amazing thing, there is still a lot of work remains to be done here. So I think I will stop here. I went over my hour time. Acknowledge all the sponsors and any question, feedback in the room, Zoom, I'll take it. Thank you very much.